We are happy to have Pieter Moree today. He's from Max Planck, Bonn, and he's working on number theory, analytical and algebraic number theory. And today he's going to talk about Euler Kronecker constants and cusp forms. Thank you, Peter, and go ahead, please.
Yeah, so it's a pleasure to talk about a topic that I really like already. It started, my interest started in it in some sense when I was doing my PhD thesis. And over the years, I've been returning to it. And in some sense, it has to do with a competition between two mathematicians. So it's a mathematical competition. They give some formula to estimate things, and the question is which estimate is actually better. And we will see that there is a huge class in some sense of these type of approximations, and one comes from Landau and one comes from Ramanujan. And in some sense, the competition is between two very unequal persons, because Landau came from a very rich family, had the best possible start in terms of education and so on. On the other hand, of course, Ramanujan, who was desperately poor, and so they were very different persons. Also, in terms of mathematical precision, Landau was very notorious for being extremely precise, and everything had to be very clearly proven. And Ramanujan, of course, was jotting down lots of things in notebooks, and so that was a huge difference. So what I'm going to report on is work with Alexandru Ciolan, who did his PhD thesis with Catherine Brinkman. So she works on modular forms. So therefore, I had the idea to do some project on modular forms with him. So he's working here this year. And the other person is helping with the computational aspects. So he's doing very extensive calculations. So he has a huge experience there. So I think he would be the world's best person in computing Euler Kronecker constants numerically. And our project it's still not finished, but I mean the results are written down. The proofs are there, so but there are various smaller aspects we want to work out. So it's still in preparation, and so it's based actually also partly on some earlier works I did in this direction. So this was namely work with Florian Luca, who actually currently is at Max Planck for 1 month, and Kevin Ford. And so what was this? This was where we looked at the Euler phi function being not divisible by a certain prime, and the distribution of Euler Kronecker constants for cyclotomic fields. And so, as you see, this was published already quite some time ago in 2014. So this will play an important role, and I will also explain some results from there. And the other thing is an unpublished manuscript of Ramanujan. And so here you see me in the library of Trinity College, where I'm actually holding this unpublished manuscript. So we had some meeting of institutes, mathematical institutes, and I was representing Faltings, and we got to see various treasures in the library of Trinity College. And so some were books of Newton. So the books behind me, those are the books that belonged to Isaac Newton, and in many he wrote comments. And there were various manuscripts that were put at display. One was a manuscript of Ramanujan. And so I did not look so closely at the text, but I just was in awe and looked at it. a little bit from a distance, and then I was surprised that I was allowed to leaf through it. So I started to leaf a little bit through it, and then suddenly I saw something familiar. And then I realized, this was a statement of Ramanujan that I disproved in 2004. So this is the unpublished manuscript is full of amazing identities on Fourier coefficients and congruences. And so it was finally published by Bruce Burnett and Ken Ono. And what I did was published in 2004. And so the present talk in some sense is a fusion of those two things and a considerable extension of the earlier work. So here's the overview, and as you see, this is very ambitious, but I will try not to talk too fast, and just likely we'll have to stop at some point. So some of the later parts here are not so relevant or are not so important as some of the earlier ones, of course. So I will tell you what an Euler Kronecker constant is, then give some historical background, which, as you can guess, is quite interesting here. Then I will tell something about Euler Kronecker constants in general, and then I will say something about the cusp forms and certain very special congruences that are valid for certain special primes, the so-called exceptional primes, and those were classified mainly by Swinnerton-Dyer with help of Serre. So that work is already quite old by now. And then what we do is our new result is that we prove something on Euler Kronecker constants for those exceptional primes. And the other new thing is that we did some Euler Kronecker constant for sums of divisor functions. And so what is the connection between the two things? The congruences actually involve sums of divisor functions. So it's not that a priori I'm so interested in the sum of divisor functions, but it's more that I'm interested in the Fourier coefficients, and so it's for that reason that we look at the sum of divisor functions. So then I'll tell you something about the proof ingredients very briefly. Given how technical everything in principle is in our present paper, I go back to the 2040 one, where in some sense there is a baby example. And then if I have time, I will say something about the Euler Kronecker constants for cyclotomic number fields that are also Euler Kronecker constants for subfields of cyclotomic number fields. That is, abelian fields play some role, as we will say. So this is roughly the overview. Well, the starting point, of course, is the Euler constant that you all know. That's of course one of the basic constants in mathematics. And actually, coming back to Landau and Ramanujan, what we will see is that the fact that the Euler constant is larger than a half plays an important role. And so here we have three mathematicians. So that's of course Euler, and the middle one is Mascheroni, who computed the Euler constant with 20 decimals. But apparently he made a mistake, so this was at the 12th decimal. So actually there is a very nice article, a pretty recent article by Legarius. So it's a nice survey paper in the bulletin of the AMS, and so it's about the Euler constant. And Legarius is actually saying that in his opinion, the name Mascheroni should be left out. And so the third person is a Dutch mathematician called Stiltus, Thomas Jan Stiltus. He generalized the Euler constants in the following way. he looked at the Laurent series expansion of the Riemann zeta function. So as we all know, it has a simple pole in S is 1, and it has residue 1 there. So that gives you the first term, 1 over S minus 1. And then you can expand it, and this expansion involves constants, and these constants are called Stiltus Constants, and a formula for them is given by this limit. So, and in particular, you have that it actually looks like this. So we have some polar part, and then we have a constant part, and then we have terms of order S minus 1, which will tend to 0 if S tends to 1 from the right direction. So yeah, this is a slight generalization. Now the Euler Kronecker constant. So the initial definition, I think this was maybe due to Ihara. This is related to the Dedekind zeta function. So given a number field K, we can look at ideals, and we can look at the norm of those ideals. So that's indicated here by the norm. And so we can form this function. And as you already see, this is very similar to the Riemann zeta function. So if my number field is just the rational numbers, then the ideals are basically just the ones generated by the integers. And so basically then I get the Riemann zeta function. Again, as before, we can look at the Laurent series. The residue is not 1, but it's a much more complicated thing. And actually it's a very interesting invariant of the number field. Or actually, it's a combination of invariants of the number field. So it involves the class number, it involves the regulator. So it's a highly important quantity, and therefore, in some sense, it's a very natural question that if we continue the expansion, do the constants we get, which are then invariants of your number field, do they say something about the behavior of that number field? And in some sense, it will turn out that it's not so strongly the case for the constant here, C0, but still, it carries quite a bit of information. And the definition of the Euler Kronecker constant is then just the ratio of these two. So it's the ratio of this constant term over the residue. And you might say, oh, that looks a bit strange. Why not just look at this C0? The answer is that in various formulas, you get something very nice actually if you look at the ratio. And it's not so natural to look at C0 itself. Also, there is some connection between the two, so that if you look at the ratio, the variation you get is far less than when you look at it separately. So therefore, we have to look at this ratio. You can give an interpretation of this, which is my personal definition, so to say, of the Euler Kronecker constant. Namely, you look at the logarithmic derivative of the Dedekind zeta function. So this has a polar part, and then it has a constant part. So the Euler Kronecker constant is the constant part in the Laurent series of the logarithmic derivative of the Dedekind zeta function. So, and if we do this for the rational numbers, then we get the Euler constant divided by 1, because the residue was 1. So we just get the Euler constant. So now let me tell you something about the historical background. So, I mean, initially what I'm going to tell you looks as if it has nothing to do with the previous story. So you need a little bit of patience. And so here actually the approximations that I told you in the beginning, why I had these two pictures of Landau and Ramanujan come into action. So Landau, he looked at the integers less or equal than x that can be written as the sum of two squares. So and he derived an asymptotic for that. And the asymptotic is that it grows as a constant, and now called Landau-Ramanujan constant, times x over square root of log x. So he proved that in 1908. Then we come to Ramanujan and 1913. What was 1913 the case? That was the year that Ramanujan wrote his first letter to Hardy. And this contained many mathematical statements, and some of which Hardy could classify, and some were known and so on, and some were totally mysterious. And here was one of the statements of Ramanujan, namely that the counting function for the sum of two squares, that it grows as that it should be very well approximated by this integral. And in addition, you have some error term, and basically Ramanujan was claiming that the error term is very small. So when Hardy wrote back to Ramanujan, he asked him to clarify what he meant with the error term, because he was a bit vague on the error term in the first letter. And so then he clarified it. But for the purposes of our talk, we can set it to be this number. So these are the two approximations we can make for this function. We can approximate it by this function, and we can approximate it by this integral. And then, of course, you can wonder which approximation is actually better in the end. So Shanks in 1964, he actually showed that this claim is false. So the thing is that what you can do here by partial integration, if you partially integrate this, the first term will be x over square root of log x, so precisely as the term given by Landau. But the next term will be something like x over log x to the 1.5. And this has some constant, and the constant that's predicted by this formula here just doesn't match the true constant that was found by Shanks in 1964. So therefore, Ramanujan's claim is asymptotically correct, but false if you take it more precisely. So in this unpublished manuscript, what Ramanujan did is he made similar claims to the one above. So so Ramanujan was very interested in modular forms and mock modular forms, and the basic modular form is the delta function, which was already considered way before Ramanujan. And so for our purposes, in some sense, it's enough to define it in this way, which doesn't make clear why it would be such an interesting function, but it's enough to define it in this way. So and then we have these coefficients tau of n, and so this is the Ramanujan tau values. And the thing about Ramanujan was that he was one of the first, or maybe the first person, to be very deeply interested in the properties of these coefficients tau of n. So that was not done before him. So, and therefore, in some sense, it's appropriate to call this the Ramanujan tau function, although the function itself was already considered in the 19th century. And so he was interested in all kinds of properties of this tau function, and one thing was congruences. And the most famous of these congruences, and very likely all of you have seen this, is that tau of n is congruent to sigma 11n modulo 691. So this is a sum of divisor functions. So this will be one of the main actors in this talk. And yeah, so you look at sums of divisors raised to a certain power. And so this tau of n is a complicated arithmetic function, but modulo 691, you get something very simple, because this is pretty simple to analyze. So that was the statement of Ramanujan.
Peter, can I have a question? Ramanujan knew about the formula of delta in terms of Eisenstein series E4 and E6.
Yeah.
He knew this delta is equal to E4 to the 3 minus. Okay.
Sure. Yeah, you will see that actually he was working all the time with E4 and E6 and so on. Yeah. But I mean, yes. So yes, he worked continuously, basically with E4 and E6, but he had another notation for it, as we will see. So what Ramanujan did was, so he realized that there is this congruence, and also he found congruences for other primes. And so these are what later will be the exceptional primes. And then the whole theory was based that basically explains where these primes are coming from. And this theory was set up by Serre and Swinnerton-Dyer. And so, okay, so given this function tau of n, here comes his statement. So what we do is we set t sub n to be 1 if the prime q doesn't divide tau of n. So think of 691, and we set it to be 0 otherwise. So basically he was interested in the divisibility of tau of n by some prime q. But for analytical purposes, it's actually better to focus on non-divisibility. That turns out to be the more natural thing. And the idea is to show that it doesn't happen too often that tau of n is not divisible. So in this unpublished manuscript, he wrote, it's easy to prove by quite elementary methods that basically for a set of density 0, tau of n is not divisible by q. So the point is, his statement is basically that tau of n is divisible by 691 for almost all integers n less or equal than x. So for a set of density 1. And okay, then he continued to write that it can be shown by transcendental methods that there is the following asymptotic here. And then he went beyond the asymptotic. Then he wrote down his favorite integral type of expression, and he claimed that there is a very small error term. So this looks very similar to the sum of two squares thing. Yeah, and so what is this delta q? For every q, this is some rational number that he explicitly gave. So for 691, for example, it's 1 over 690. So that's, yeah, and for 5, for example, it's a half. So that's also understood now, of course, what is delta q is. And so Rankin, that was a mathematician who was always interested in these congruences, and he did various papers related to it. So yeah, with him I share this interest for the congruences, because the congruences is one aspect maybe that is not so well studied in number theory as certain of the other properties. But yeah, so there are some pretty famous mathematicians that were interested in that before me. So this paper I mentioned in the beginning of 2004, what did I show there? That actually for the special primes that Ramanujan found, his claim is false. So this is an analog of the Shanks result for the sum of two squares. So what was the claim? The claim is that that there is a very precise estimate for how often this is not divisible by one of those primes q, and so this asymptotic form that was given by Ramanujan, who wrote down some explicit formulas for these constants c sub q. That's known to be correct, but on a more precise level, what he did was not correct. And in some sense, so how does the proof go? In essence, by computing certain Euler Kronecker constants with a prescribed accuracy. So, but I will come back to this. Well, I mean, on the occasion where I had this huge pleasure and huge thing to remember, that I could hold this manuscript in my hands, I of course made also a picture of the place in the manuscript where this formula, where this statement appears. So I mean, here you see it. So I hope you can read it. Can read this. Yeah, so here you see it can be shown by transcendental methods that, okay, so he doesn't completely write sum, so maybe I should even try to bring this more into the form of the unpublished manuscript itself. But the essence of it is what I wrote down there. And here you see that he gives this error term, so where R is any positive number. Yeah, so that's what I disproved. Okay, now I come back to the Euler Kronecker constants, but in a more general setting. So Ihara had looked at it in the setting of Dedekind zeta functions, and we will come back to this Dedekind zeta function. Oh, by the way, can you tell me if at some point if I have only 5 minutes left or something? Then that would be good. I always tend not to watch the time. Okay. Just warn me, and then I will find some natural ending.
That's okay.
Okay, so so I want to tell you about the Euler Kronecker constants in a more general setting, and so this is the setting I defined. And so this is for sets that I call multiplicative. So think of a set of natural numbers, and I call it to be multiplicative. If you take two co-prime numbers, the product is in that set. But also if you have a number in it and you have two co-prime factors, then both of these co-prime factors are in your set S. And an example is, where you take, say, all the primes congruent to 1 mod 4, you take the prime 2, and you take the square of all the primes congruent to 3 mod 4. You can multiply all these things together, and this gives you so-called multiplicative semigroup. And so what is that multiplicative semigroup? That's nothing else but the integers that can be written as sum of two squares. So I'm referring to the result of Fermat that which integers can be written as a sum of two squares. Well, they can have any factor of 2, any prime factor congruent to 1 mod 4, and all the prime factors congruent to 3 mod 4. They must appear to even powers. So that's one example of a multiplicative set. And another one creates an enormous set of examples, namely, we take any multiplicative function and we take any prime q, and we look at a set of integers such that f of m is not divisible by q. So since every talk has to contain at least one proof, here comes the proof. Let's look at the non-divisibility of the multiplicative function f of m times n by q. So since it's multiplicative and m and n are co-primed, this thing here is the same as this thing here, so we need Q not to divide this, which is the same as Q is not dividing f of n and Q is not dividing f of n. And so this means that n is in your set S, this means that n is in your set S, and this means that the product Mn is in your set S. So this is a huge class of gives you a huge class of multiplicative sets. And of course, okay, what I didn't tell you is that the tau of n is a multiplicative function. So we can take tau of n, we can take q to be any prime, and then we have a multiplicative set. Okay, and now I'm going to define the Euler Kronecker constant for such a set S. And so the idea is I look at the primes in S less or equal than x. So that's denoted in this way. I think I should have removed the notation here and just written it out directly. And the idea is this goes as some constant delta times the number of primes less or equal than x. So you can think, for example, of the integers that can be written as a sum of two squares. So what are the primes that are in the set S? It's the prime 2 and it's the primes p congruent to 1 mod 4. And so we know then that this is density half. So in this case, we have delta is a half. So now, given that this holds, you can look at the generating series, the L series defined in the following way, and then we can look at the constant part of the logarithmic derivative, and here you have to add the appropriate part so that this limit actually exists. So if you remember what we did for the delicate zeta function, it was precisely the same thing. We took for this LS, we took the delicate zeta function. Here we had this derivative. The delta is 1 in that case, and then this gave the Euler Kronecker constant for the number field K. Okay, so this is the general Euler Kronecker constant idea. And under the conditions on S, what you can show is that the counting function, so now we're counting all the elements in S. So in the first example, it would be all the integers n that can be written as a sum of two squares. And well, then one can prove that there is an asymptotic of this form. So for the integers that can be written as a sum of two squares, the delta was a half. So here I get 1 over square root of log x. So this gives you indeed the Landau formula. And we can now consider the Landau approximation, which would be this form. This for me is the Landau approximation. So it's the direct asymptotic. So that's this term. On the other hand, I can look at the appropriate integral form. So that would be this form. And then you can look at the difference with the actual function. And then the question is, if x tends to infinity, what's the better approximation? Is it this asymptotic, or is it the integral term? Oh, I think actually a t here is missing. So yeah, this is the idea, and yeah, this is the Landau approximation versus the Ramanujan approximation, and which one is better? Okay, and this is going to depend on the Euler Kronecker constant. So if you look at a more precise way at this counting function f of x, then it has this asymptotic. But you can look at the second order term, which is of this form. And then it turns out that we have this constant, which is equal to 1 minus delta times 1 minus the Euler Kronecker constant. So that's what the reality is in this case. And the criterion is then eventually that the Ramanujan approximation is better if the Euler Kronecker constant is smaller than a half, and it's lambda wins if the Euler Kronecker constant is larger than a half. Okay, so I can explain you where this is coming from. This is very easy to see given this formula here. Namely, if I look at the integral, the Ramanujan form, then I can just partially integrate it, and then as a second order term, I just get 1 minus delta. Yeah, and thus the asymptotic approximation basically gives you at this point 0. So lambda says it's 0, Ramanujan says it's 1 minus delta, and reality says it's 1 minus delta times 1 minus gamma. And then from that you arrive at this criteria. So of course, if my gamma would be 1 here, then this thing would be 0. And that means that we are really on the side of the lambda approximation. On the other hand, it also means that if Ramanujan is correct, in essence, what he is saying is that some Euler type of constant is equal to 0. So that's a pretty wild statement. And so if you think of this as the usual Euler constant, so likely some very transcendental number, then he's saying that there is a very simple formula for some very simple transcendental number. Okay, so this is the general setup for the Euler Kronecker constants. And now let me state you where we were in 2014. 2014, of course, we have the sum of two squares, and Schenck disproved it for all the special primes for the tau function. I disproved it. Then in 2014, we also looked at the non-divisibility of the Euler-Totient function. Yeah, the Euler-Totient function is a multiplicative function, so you can play the same game. But the idea here in this project was to do it for an infinite family. These are just very few, just a finite number of examples, but here we're looking at finitely many primes Q. And so this was the status of the Euler Kronecker constants in 2014 when I published my paper with Luca and Kevin Ford. Okay, now I go to the exceptional primes Q. So this delta function is a cusp form, and in some sense it's the simplest one. So it has weight 12. And there you have a space of cusp forms, and that's a finite dimensional vector space. And for weight 12, it's one dimensional. In general, for every even number bigger than 12, I think you will have some cusp forms, but the space of cusp forms is not necessarily one dimensional. And it turns out that you have a very nice property, so that the Fourier coefficients become integers, they're multiplicative if this dimension of the space of cusp forms is 1. And so this happens only in finitely many cases. Yeah, and so I'm talking here about cusp forms for the full modular group. You could also try to play this game for subgroups of finite index. But here there turn out to be six cusp forms, and I give them in the notation of Ramanujan. So coming back to the question of Hossein about E4 and E6, those were denoted by Q and R by Ramanujan. And the Fourier coefficients, they involve this sum of divisor functions. So before we saw the 11 powers, and here it's just to the power 3, and here it's to the power 5. And this, of course, is the connection between E4 and E6 and delta. Yeah, okay, I should have given them maybe in terms of Q and R to be consistent. Okay, now I come to the classical properties of the Fourier coefficient. So of these 6 cusp forms, I can look at their Fourier coefficients, and we denote them by tau sub k. So k is the weight. And it turned out that these coefficients are integers that are multiplicative. They satisfy this recursion, and they satisfy this inequality. And the amazing thing is that Ramanujan, on basis of not very much data, he conjectured all these properties. And some of these properties actually, to prove it, that kept mathematicians busy for an enormous time. Well, not the first one, for example, that was proved more or less 1 year later, but this last one is an incredibly famous result. And for weight 12, it was proved by Deligne, I think, in 1974. And this was really considered to be a masterpiece of mathematics of the previous century. And I like this book by the Murthy brothers. And so it's called The Mathematical Legacy of Srinivasa Ramanujan. And it starts actually with a discussion of the properties of the Ramanujan tau function. And then it continues to describe the influence of this in modern mathematics. So these properties that Ramanujan saw actually played an enormous role later in mathematics. And also the interesting thing is that at the time that, for example, Hardy, he didn't realize how important some of the things were that Ramanujan did. That only became clear later. Okay, so Serre and Swinnerton-Dyer were the main person.
Sorry, Peter, one question. Yeah. Here, tau k are the Fourier coefficients of the modular form, the cusp form that are in this weight, or they are the coefficient? I just hear these taus are the Fourier coefficient for the delta, or not for all the cusp forms?
No, for these functions. So, for example, for 18. So tau sub 18 would be the Fourier coefficient of this function.
Yeah. Okay. Thanks.
And so on. Yeah. So and basically what I called tau n before is tau sub 12 n in this new notation.
And all of them are eigenform as well, or not?
Sorry?
Are them eigenforms for operators or not? You don't know.
All of them are what?
Eigenform.
All of them are integers satisfying these properties. These properties here, but of course these are integers of a quite complicated nature.
Yeah, thanks.
And so what Serre and Swinnerton-Dyer did was to create a systematic theory of these congruences. So for these special primes, 2, 3, 5, 7, 23, and 691, Ramanujan had written down some congruences, and after him, various other mathematicians started to look for congruences, also for other cusp forms. Already Ramanujan himself did that in the unpublished manuscript. So this became a game to do that, and what arose was something quite unsystematic, and so then Serre and Swinnerton-Dyer came and they created a theory, so the Allergic representation theory, and with this theory they were able to classify certain type of congruences. So, for example, this one. For 691, that's the one that we saw before. So the V would be 0, the K is 12. So then we have sigma 11 of n. So in essence, this for 691 is an example of a congruence of the first type. Apart from that, the congruences of the second type. So this looks quite differently. And this is for tau of n, this would be for 23. And there is one congruence known of this type, and it was not found definitively by Serre and Swinnerton-Dyer. That was by Haberland using developing Galois cohomology. So we could not compute the Euler Kronecker constant for this one, so this is left open, but here we can deal with all these examples and compute the Euler Kronecker constants. An important observation is, it's elementary, but I cannot say it in a few words, if if a prime q does not divide this sigma 11 of n, even only if it doesn't divide this one, where you just take the greatest common divisor of L and Q minus 1. So you can make a huge simplification. So so of all these the sums of divisor functions, if you look at it modulo Q, there are only in essence finitely many possibilities that play a role in terms of non-divisibility. So I mean, here I indicate this, I use that symbol to indicate that it's not a true congruence. But what is true if the left side is divisible by Q, so is the right side, and if it's not, then the right side is also not divisible by Q. So that's enough for our purposes. Okay, and so then there was the question of finding all those exceptional primes. So yeah, so where are the exceptional prime suspects? So they were classified, and it turns out that there are two important subcases, namely where the prime q is bigger than the weight. So the example 691 is of that type. That's of course clearly prime bigger than 12. And so it turns out that you have these cases, and it turns out that this coefficient is congruent to such a sigma function as before, and you can reduce it to something like this with an R, which is the greatest common divisor of k minus 1 and q minus 1, and usually it's 1. So usually this is just the sum of divisors to the first power, and you can look at an divisibility of both sides. Yeah, so the one we saw in the beginning is just this example. What is interesting to note is that these numbers appear in numerators of Bernoulli numbers. There is a reason for that. It's basically that modulo 691, the E12, the Eisenstein series E12, which has a constant term which involves this Bernoulli number, becomes that constant becomes 0, and in some sense the Eisenstein series becomes a cusp form. So that's the essence of this congruence. So these are the ones for q greater than k. They were classified. Here is the case q smaller than k. They are classified. The difference is now that you have an n here, and so this lists all the cases where q is smaller than k. But for example, what does the no mean here? It means that there is no congruence for the prime 11 for the delta function. There is no special congruence. So these were our basic data. Then let me remind you of the Ramanujan claim. So he was looking at the non-divisibility of tau of n and other cusp forms, and so this tk is 1 if you're, the notation is very unlucky here. So basically it's the indicator function for the non-divisibility, and so this was the statement, and our main result then is that we classified. So this is the main result, that we classified for all those 6 cusp forms whether the Ramanujan approximation is better than the Landau approximation. And actually what we did is we computed the Euler Kronecker constant in each case, except for the congruence of type 3. That's a very special one where you would get Artin L series involved and derivative of Artin L series. So that would be challenging to do that. And okay, so whatever, you find some results. So that's not really the point I want to make. But we find this as an application of the non-divisibility of the sums of divisor function. Yeah, so this is the sum, the k powers of the divisors of n. You sum that, and that's sigma k of n. Maybe I should have clearly written down some definition somewhere. And in this story, a subfield of the cyclotomic field plays a role, and this we call k sub m. So it's the unique subfield of degree q minus 1 over m. So k1 is of course the full cyclotomic field, and k2 has then degree q minus 1 over 2. And so this is the maximal real. That's the maximal real subfield, for example. So those fields play a role. Then we have the Dedekind zeta function that we saw before. What we will get is, and you can immediately forget that, but just to see that you get some complications. So there is some very horrible function involved that one unfortunately has to analyze to some part, how quickly this function actually goes to 0. For fixed r, it goes to 0 with growing q, and you have to analyze how quickly it goes to 0. So this is rather horrible. And so I can say a little bit more about this field k sub m that come into the picture. So you can write down factorization of the Dedekind zeta function. So this reflects basically how primes split in such a field. So in the field k sub m, the primes that satisfy p to the power m is congruent to 1 mod q are the ones that split completely. So in k2, this would be the prime such that p squared is congruent to 1 mod q splits completely. And this are, of course, the prime such that p is congruent 1 or p is congruent to minus 1 mod q. Those are the primes that split completely in that field. And so the Dedekind zeta function has a factorization into the Euler L series, which is written down here. The Euler Kronecker constant you can express as this type of limit. And the limit, if you want to do that, you can also write in terms of primes. And as you then get from here, I mean, the behavior of such a constant is very much influenced by the small primes that satisfy this condition, because this term is big if my prime is small. So if there are many primes p such that p to the m is congruent to 1 mod q, then this term will be big, and this tends to be negative. So there is here a big contribution from the irregularities in the prime distribution. So if you have such a very irregular situation, where you have lots of primes congruent to 1 mod q following each other, you will get quite a negative value of this Euler Kronecker function. So it's a measure for irregularity of prime distribution. Okay.
You mentioned that you have 5 minutes.
Okay, that fits. Then I can formulate a result for the sigma k. Okay, so now I can formulate the main result. So we're looking at the q non-divisibility of the sums of divisor function and this variant with the n in it. And this variant is motivated by the application. And okay, so we give some asymptotic formula, and then the second order term is related to the Euler Kronecker constant, and the Euler Kronecker constant satisfies this formula 4. So here we see that the Euler Kronecker constants of certain subfields enter the game. Here there is the horrid expression. This is just very innocent, and this is the gamma itself. So and yeah, these things you can compute, and so you can do that for the other function as well. And if you want to do Ramanujan versus Landau, you have to look at the usual criterion, greater or bigger than a half. I want you to show you some tables. Okay, so I might skip this. We can also do Landau versus Ramanujan for all the cases where k and the greatest common divisor of k and q minus 1 is 1, because we saw that that is the most common situation where this r was 1. And so you can completely classify that, and really there goes a lot of computational number theory into that. Okay, so what is the outcome then to finish my talk? So these are the Euler Kronecker constants for q greater than k. And this was partly highly non-trivial to compute that. So here for this biggest prime, Alessandro, who, as I told you, is a super duper expert in doing this, has a big cluster available in the University of Padua. His computer system took 6.5 days to compute this with this precision. So that's a very difficult computation, partly because this very disturbing term SRQ behaves in a very bad way. But yeah, he was able to manage them. The red one are the numbers that I computed, but they were now computed with higher precision. So, and this is for q smaller than k. Then there are not so many cases in the end you have to compute, because there is a lot of repetition. So therefore you only have to compute these cases. Of course, for me, it was very exciting to learn if my computations, since I'm not so into computer calculations in 2004, were correct, but luckily they were. So that was very good. Is it now minus 1 minute? Okay. So I think I will stop then here.
Okay.
Okay, thank you very much. So, thank you for your interesting talk. And are there any questions?
Peter, what are, maybe just general question, what are the difficulties to do for arbitrary cusp form, which is eigenvector of all Hecke operators? I mean, all of them, they have this multiplicative properties.
Mm-hmm.
And why? I mean, you choose some 7 or 6 examples of cusps, or no?
Right. Now, this is absolutely excellent question. So why can't one do this in absolute generality, or rather, why can I not do that in absolute generality? The thing is as follows. I mean, the whole thing is based on the fact that the generating series, so this L sub S, that actually, if you take it to an appropriate power, it's just a zeta function times Dirichlet-L functions times some well-behaved vector. And the thing is, and so this is related to the fact that this non-divisibility is precisely characterized by primes being in arithmetic progression or not. And as long as, if you don't have that, say it's determined by some Cherepaterev type of condition, which it is in general, then your L functions will be objects of a much greater difficulty. So you would have, say, Hacker L series or Akin L series, and you would have to work with them. So it's a much more challenging thing to do. And the whole thing about these exceptional primes is that everything in some sense collapses, and the criterion for non-divisibility of your coefficient in prime value is just primes being in some union of arithmetic progressions, which is always related to Dirichlet-L series. And Dirichlet-L series and their derivatives one can handle computationally very well. But I mean, it's a challenging project. For example, I would be very happy if somebody could do this Haberland congruence. So there was this type 3 congruence. So that's for the prime 59 and weight 16. So yeah, so I think that will be really a challenge where one can really learn, or has to learn, quite a bit of number theory to do that.
Okay.